Welcome, curious minds, to another deep dive. Today we're plunging into a challenge that, well, I guarantee most of you, if you're deep in the machine learning world, have really wrestled with. I mean, the sheer, often grueling labor involved in developing and iterating on high-performance ML models. Think about the effort, right? Whether you're building a robust tabular classification system or maybe tackling image denoising, it's this constant cycle. You're always experimenting, wrangling data, tweaking features, optimizing code. It's a heavy lift, even for seasoned experts.
It absolutely is. And lately, we've seen this really fascinating shift in how we think about tackling it. Large language models, LLMs, they've kind of emerged as potential machine learning engineering agents, MLE agents. The core idea is incredibly compelling. View these complex ML tasks as basically sophisticated code optimization problems. The LLM, with all its power in code generation and reasoning, sort of takes on the job of generating, debugging, refining the Python scripts.
Yeah.
Sounds like the dream, right? Automating away all that effort.
It really does sound like a dream. But, like with many new technologies, the reality hits some bumps. These early LLM-based MLE agents, while they're super promising, they've run into some, pretty significant obstacles. The first one, and maybe the biggest, is this heavy reliance on the LLM's own static knowledge. This often means they lean towards familiar methods, sometimes even outdated ones. Like, you ask it to do text classification, it might suggest logistic regression, because that's all over its training data. Even though, modern transformer models will blow it out of the water, it's like its knowledge is locked in the past.
Exactly. And that connects directly to the second big limitation. Their exploration strategies are often quite coarse. Current agents, when they try to refine the code, they often modify the whole script structure at once. Big chunks. This sort of broad brush approach, it prevents the deep, targeted digging needed within specific bits of the pipeline. Say you want to experiment deeply with feature engineering options, maybe different scaling methods or interaction terms. But every change means the whole model, the training loop, everything gets rebuilt. It's just inefficient. And this often leads them to jump to other stages like hyperparameter tuning way too early before a key part is properly optimized. They lack that surgical precision.
Right. So if you want something smarter, something that can adapt and really push the state of the art, we need a different approach. And that brings us neatly to the star of our deep dive today, MLE-STAR. This is a novel multi-agent framework built specifically to tackle those challenges we just laid out. Its unique angle is integrating external web search, getting real-time knowledge with a really systematic, targeted refinement of specific code blocks. So it's not just using what it knows, it's actively looking for the latest stuff and applying it precisely.
Mm-hmm. And our mission today is to really unpack this MLE-STAR framework. We'll dig into its innovative multi-agent architecture, look at each agent's job. Then we'll dissect the empirical evidence. How well does it actually work? How does it get medals in 64% of Kaggle competitions on MLE-bench Lite? This isn't just about automation. It's about seeing what these LLM agents can really do on complex ML tasks. We'll provide a deep overview, assuming you've got that expert background in ML, data science, and math.
Okay, great. So let's set the stage first by looking at the broader context. Automated machine learning. AutoML, it's not a new idea. The whole field has been trying to reduce how much human expertise we need by automating parts of the ML pipeline. We've seen systems like AutoWeka, it was quite early, automating algorithm selection and hyperparameters. And TPOT, using genetic programming. More recently, AutoGluon, which is super popular and effective, especially for tabular data, right?
Yeah.
Stacking models and all that. They've definitely done a lot of the heavy lifting in searching predefined spaces.
They have, absolutely. These traditional AutoML methods, they've undeniably pushed the field forward, made things more accessible, but they consistently hit this fundamental bottleneck. They usually rely on these predefined, sort of manually engineered search spaces, like AutoGluon might explore a fixed set of models like GBM, XGBoost, CatBoost, and a set range of hyperparameters. But who defines those spaces? Often, it still takes a lot of domain expertise, human effort to curate those lists of algorithms, pre-processing steps, hyperparameter ranges. So while they automate the search within that space, defining the space itself, that's still a human job, limiting their autonomy, especially for really novel problems.
That's the exact gap the LLM-based MLE agents are trying to fill, isn't it?
Yeah.
They aim to address that limitation by exploring directly in the code space. Instead of needing these rigid, curated search spaces, they use the LLM's coding and reasoning skills to navigate the huge space of possible Python scripts. It's a fundamentally different, potentially much more flexible way, moving beyond fixed templates.
Yes, precisely. And if you look at the broader landscape of LM agents, you can see this evolution. You've got general ones like React, combining reasoning and acting with external tools. Hugging GPT coordinates different models. They show LLMs can plan and interact. Then you get specialized ones like Voyager and Minecraft, or IFA for competitive programming. What's cool about those is how they learn iteratively from feedback in their domain. MLE-STAR sort of builds on that, but specializes right into the complex, iterative world of ML engineering tasks, learning from its own code executions.
Okay, so focusing specifically on ML engineering, we've seen agents like AID, MLab, and DS Agent trying to automate things. Let's talk AID first. My understanding is it uses a tree structure to explore the code space. What are its main drawbacks for someone looking for top-tier results?
Right. AID uses that tree structure, which is innovative for exploring code paths, but it fundamentally leans too heavily on the LLM's internal pre-trained knowledge. This often means it picks models or algorithms that are well known, but frankly outdated or just not optimal for state-of-the-art performance today. Take image classification. AID might default to ResNet from 2015, not because it's best now, but because it saw it a lot during training. That's a big issue when ML moves so fast with new models popping up constantly. Plus, its refinement process, it can jump around between pipeline stages too quickly. Instead of really deeply optimizing, say, feature engineering, trying lots of transformations, it might just take a few stabs and then pivot to tuning hyperparameters or even trying a totally different model. It doesn't quite have that persistence, that targeted depth.
Right. That makes achieving really competitive results difficult. What about DS Agent then? I know it uses case-based reasoning, pulling from curated examples, often from Kaggle. Sounds like trying to mimic past human successes.
DS Agent is interesting, yeah. It's almost like a very sophisticated copy-paste adapt system. It draws on this pre-built bank of manually collected examples, often high-scoring Kaggle solutions. Then it tries to adapt those cases to new, similar problems. But its big weakness is scalability and adaptability, that manual case bank. It takes huge human effort to build, categorize, and keep updated, especially as new tasks and data types appear. Its static nature means it really struggles with truly novel task types. Like, give it a complex, multimodal problem with, say, tabular data and audio streams. If there's no case like that in its bank, it's kind of stuck. Plus, solutions pulled from a fixed bank can sometimes overfit to the specifics of those original problems, making them less robust on new scenarios, even if they seem similar.
Okay, so this is really where MLE-STAR steps in to differentiate itself. It's designed to overcome exactly those issues. The static knowledge, the inflexible cases. How does it formally set up the problem, and what are the key contributions that bridge those gaps?
Exactly. MLE-STAR frames the ML engineering problem formally. Find an optimal solution S, which is just a complete Python script, by maximizing some score function H. That function H could be accuracy, F1, RMSE, whatever fits the task. It does this using a sophisticated multi-agent framework called A. This framework A takes the dataset D and a detailed task description T task as input. Key task is key. It spells out the task type, image classification, regression, etc., data types, and the score function H. And crucially, A isn't just one big LLM. It's made of N different LLM agents, each with a very specific job. That modularity is central to its targeted approach.
So a team of specialized agents, not just one trying to do everything. And the core difference is how it links external dynamic knowledge with that targeted component-level refinement. How does MLE-STAR actually explore options for the specific pipeline parts, hitting those limitations of old knowledge and broad exploration head-on?
It's all about precision and using up-to-date knowledge from outside the LLM's training data. Unlike older agents doing broad code space searches, which can be inefficient, or relying on static case banks that go stale, MLE-STAR strategically looks for implementation options for specific, granular ML pipeline components. So instead of just searching good image classification model, it might search state-of-the-art image feature extractors or best practices for image augmentation 2024. It boosts scalability and timeliness by using LLMs together with search tools like Google Search. This lets it dynamically pull descriptions and code examples for effective modern models and technique stuff way beyond its fixed internal knowledge or a limited case bank. It means it can find and suggest methods published just yesterday, not just ones it was trained on years ago. That dynamic retrieval is absolutely fundamental.
That's a huge difference, moving from static recall to active discovery. Okay, so quick summary of the key innovations before we dive deeper. Integrates web search to beat knowledge cutoffs, uses targeted code block refinement guided by ablation studies, and has a novel ensembling method, a really comprehensive setup. All right, now that we've got the foundations, let's really get into the weeds, the nuts and bolts of the MLE-STAR framework. This multi-agent architecture sounds fascinating. Phase 1 is about generating that initial solution, and a key part is using web search as a tool. Why is that external knowledge so critical right at the start? Why can't the LLM just use what it knows?
That really gets to the heart of the LLM limitations. Relying only on the LLM's internal knowledge for model ideas, especially for competitive stuff, it just often leads to suboptimal picks. We see it consistently. LLMs, stuck with their training data cutoff, tend to suggest models that were common back then but are now outdated. Like, take a tough text classification task on Kaggle, like Jigsaw toxic comment classification. An LLM without web access might suggest basic logistic regression or an old SVM just because they were documented heavily in its training. But the state of the art now, it's dramatically shifted to transformers like BERT or Roberta. The performance gap is massive. The key insight MLE-STAR uses is that for top performance, agents need to break free from static knowledge. They need real-time access to the latest stuff. And that's exactly what the Retriever does by tapping into the web. It's like switching from a textbook to browsing Stack Overflow for the newest solutions, but done automatically.
Makes total sense. Got to overcome that knowledge cutoff for the bleeding edge.
Yeah.
So how does MLE-STAR actually find these candidate models? Walk us through the roles of those initial scouting agents, Retriever and AINIT.
Sure. So MLE-STAR kicks things off with an Retriever agent. Its job is to dynamically query a search engine, usually Google search, to find M-effective state-of-the-art models relevant to the task description T-task. The way Retriever is prompted is crucial here. It asks targeted questions like state-of-the-art image classification models 2024 or best deep learning models for tabular data. This process is formally written as T-model, T-code MU1, a Retriever, T-task. For each model manually finds, it gets back a pair, T-model, which is a short description like efficient at B7 for high-res images, and really importantly, T-code, which gives example code snippets. That T-code is vital because the LLM might not know the exact implementation details for newer or less common models. Without that code guidance, it might struggle to actually write working script.
Ah, okay. So it's getting not just a name, but practical code help too. Then, once it had these M candidates with their code examples, how does the init agent step in to evaluate them and make initial scripts?
Right. After a retriever finds the candidates, the candidate evaluation agent AINIT takes over. For each of the M models, and its main job is to generate a complete working Python script, let's call it SINIT, to solve the task using that specific model. It basically synthesizes the T-task requirements, the T-model description, and critically uses those T-code snippets to make sure the script actually works and implements the model correctly. Formally, SINIT, AINIT, T-task, T-model, T-code. Once each SINIT script is generated, it gets automatically evaluated. This means splitting the data D into train validation, training the model from SINIT, and checking its performance H on the validation set. The result of this phase is a set SINIT containing M initial scripts, each paired with its measured performance score.
That's a very systematic way to get strong starting points. So now you have M scripts based on current models found via search, each scored. How does MLE-STAR merge these into one solid initial solution? Does it just pick the best one? Or is the emerger agent doing something more clever?
It's definitely more clever than just picking the best one. It's an iterative merging procedure designed to blend their strengths. First, those M scripts in SINIT get sorted by performance, highest score first. The initial solution for this merging phase, 7, starts as the top script, spine init, and its score best is recorded. Then the other scripts, spine to init, are brought in one by one. A dedicated emerger agent handles this. Emergers isn't just mashing code together, its prompt specifically guides it to create a simple average ensemble of the predictions from the current sitter and the incoming spine. So it modifies as sitter to include the new model and average their final predictions. This process repeats. Emerger tries to integrate each spine, updating MOT and SINIT only if the ensemble performs better. It stops when adding more scripts doesn't improve Vatisin anymore. This dynamic ensembling helps create a more robust, often better performing starting point by leveraging the diversity of strong individual models.
That's a really sophisticated way to start, ensuring the initial solution is already a strong contender, potentially an ensemble itself. Okay, let's move to phase 2, iterative refinement of code blocks. This sounds like where the targeted refinement really happens, focusing on granular optimization. How does the outer loop figure out which specific code blocks to modify? What are the arable and extractor agents doing here?
Yeah, this iterative refinement is really a core innovation. It runs for T outer loop steps. In each step T, the goal is to improve the current best solution at eta Hess plus 1. The key idea is to avoid those big, inefficient changes. Instead, MLE-STAR identifies and targets specific code blocks within the script test using an ablation study. A dedicated MLE agent, an LLM prompted for this, generates an ablation script at based on Saint. This at script makes variations of ML by changing, disabling, or simplifying specific parts of the pipeline, like maybe it makes a version where a feature engineering step is skipped, or a different activation function is used. And critically, MLE gets summaries of previous ablation studies, tieable as input. This guides AML to explore different parts of the pipeline over time, stopping it from getting stuck optimizing the same bit over and over or trying variations on something already well refined.
So Emily makes this smart ablation script which gets run. What happens after that? How do you actually pinpoint the most important code block from those results?
Right. After it runs, it produces results ERT, showing the performance impact of each change. Then, a specialized summarization module. A summarize processes both the script at and its results are. A summarize boils down those results into a concise summary T-table. This summary highlights which changes helped, hurt, or did nothing significant. Finally, an extractor module extractor analyzes that summary T-table. Its job is to find the single code block AC within TIAST whose change had the biggest impact on performance, good or bad. Extractor prioritizes blocks that haven't been targeted before, using the set of already refined blocks. This ensures systematic exploration. At the same time, Extractor also creates an initial refinement plan, P0, for that block C, using insights from the ablation study. So the first refinement attempt is already informed.
That's incredibly precise. It's actually using empirical feedback to find the leverage points. So once S is identified and P0 is ready, we go into the inner loop for intense refinement within that block. How do a coder and a planner work together here?
Exactly. Once sect is defined and P0 is proposed, MLE-STAR dives into an inner loop to explore K different ways to refine just that block. And a coder agent starts things off by implementing that initial plan P0. A coder is an LLM specialized in code generation and transformation. The plan P0 isn't vague, it's structured, like a mini-spec detailing the change needed for seat. Say seat used standard scalar. P0 might tell a coder to try min-max scalar or even a custom normalization function. A coder takes seat, applies P0, and generates a refined version C0 teller. This A0T is then swapped back into the main script to make a new candidate 0T, and its performance H0T is checked immediately. For the next iterations in this inner loop, a planning agent, a planner, steps in. A planner's job is to intelligently propose the next refinement plan, PK, for the same block as seat. It uses the history of previous attempts in this outer step, the pairs of plans and their scores, PJ, HSJT, as feedback. This lets the planner learn what worked and what didn't, and adjust. Maybe it sees scaling methods work better than feature selection for this block, so it proposes more scaling variations. A coder then generates the new block, FJT, based on PK, creates the candidate ITSKI, and evaluates HSKT. This inner loop runs for K steps, really digging into refinements for SACT. After exploring K strategies, the best one, SKT, is found. The solution for the next outer loop step, S+1, is updated only if this best inner loop candidate HYT actually improved on SANE. This nested loop process is how MLE-STAR gets that deep, targeted optimization.
That systematic, almost microscopic refinement is really impressive, focusing energy where it counts. But MLE-STAR doesn't stop there. Phase 3. Ensemble strategies for more performance gains. Why is ensembling so key, and how does MLE-STAR do it differently from standard practices?
Right. The novel ensembling in MLE-STAR is based on a core idea. Even solutions that aren't the absolute best individually might have complementary strengths. Standard practice is often just picking the single model with the highest score. But MLE-STAR recognizes that intelligently combining predictions from multiple distinct solutions, even ones that weren't top scorers, can lead to better overall performance. This is a classic idea in ML, right? Ensembles like random forests often beat individual decision trees. MLE-STAR applies this meta-learning idea to the entire generated ML pipeline.
So how does it automate finding these ensemble plans? It's not just hard coding an average, it's dynamically exploring ways to combine them.
Exactly. Let's say MLE-STAR has generated L distinct solutions, LL1 general, maybe from parallel runs or different initial paths. The goal is to find an effective ensemble plan E to merge them optimally. MLE-STAR starts with a baseline. It proposes an initial plan A0, maybe just simple averaging of the final predictions from all L solutions. It calculates the performance H0 Then, for R iterations, an Ains planner agent takes over. This agent specializes in suggesting sophisticated ensemble plans. It doesn't guess randomly. It uses the history of previous attempts, the plans, and their scores, EJ/HS gens, as feedback. This lets Ains Planner learn and propose better strategies. Maybe if averaging worked okay, it suggests weighted averaging or stacking or voting, dynamically iteratively adjusting based on what worked before. An ensembler agent then implements the planner to get the ensemble results trends and evaluates its performance trends. This loop allows MLE-STAR to autonomously explore and find potentially novel, effective ways to combine complex solutions, pushing performance beyond any single one. It's like meta-optimization.
That's a huge step towards real autonomy, where the agent suggests and refines its own meta strategies. Beyond performance, MLE-STAR has these robustness modules. Sound like crucial safety nets. Let's start with the debugging agent, AidBugger. How does that work?
The AidBugger is absolutely vital for practical use. If a script as generated by MLE-STAR hits an error during execution, maybe a type error, index error, or some other runtime bug, AidBugger gets called. Its job is to try and fix the script. It gets the faulty script and the error traceback debug. AidBugger analyzes debug using the LLM's reasoning to understand the error, like parsing the stack trace. Then it iteratively proposes fixes, AidBugger, tbug. It keeps trying, rerunning the script after each fix until it works or hits a max number of debugging rounds. If it can't fix it, MLE-STAR flags the issue and moves on using the last working version, avoiding total failure. Super important for real-world scenarios where code isn't always perfect first time.
That's a critical practical piece, ensures resilience. Another big sneaky issue with LLM code is data leakage. How does the leakage checker stop that, especially in tricky pre-processing steps?
Data leakage is definitely pervasive and dangerous, especially with LLM code, which can hallucinate things that accidentally contaminate training. We've seen cases where test data gets used improperly in training prep, like calculating imputation values or scaling parameters using stats from the whole data set, train and test, not just the training part. That leaks test info into training. A leakage tackles this head on. It analyzes the script S before execution. But instead of checking the whole script, which is inefficient, it smartly extracts just the SPIDA block where data loading, splitting, preprocessing happens. It then uses heuristics and pattern matching, leveraging the LLM's understanding of data flow to spot potential leakage in snake data. Like, does it see X test being used when fitting a scalar meant only for X train? If a leakage finds an issue, it generates a corrected version, C data, making sure, for instance, that scaling or imputation fits only on training data before applying to both train and test. This C data replaces the bad part. Every solution goes through a leakage before evaluation. It's a core guardrail.
So it's proactively catching a subtle but really damaging error. Can you give a concrete example of how bad it would be without a leakage?
Definitely. Take a competition like Spaceship Titanic. Without a leakage, an LLM might create features using the target variable, say transported. That's fine in the training set, but obviously it's not available in the real test set. The LLM might hallucinate a feature creation step using transported on the whole data set. What we saw happen is misleading performance. The internal validation accuracy might jump up nicely, maybe from 0.8188 to 0.8677, looks great. But the actual performance on the real unseen test data, the final Kaggle score, would crash, maybe from 0.8033 down to 0.7343. This huge difference shows why a leakage is critical. Without it, the agent thinks it found a great improvement, but it would fail badly in reality because of that hidden data leakage.
Wow, that really drives home why these guardrails are essential. And what about the data usage checker, ADATA? What common LLM blind spot does that fix?
ADATA handles another surprisingly common LLM habit, just overlooking or not using all the data provided. Many Kaggle comps give multiple files. You get train.csv, test.csv, but maybe also metadata.csv or geometry.xyz files or external embeddings. We've seen LLM scripts sometimes just focus on the easy CSVs, completely ignoring other files that hold vital info, like those .xyz files in Nomad 2018 predicting. It's like solving a puzzle but ignoring half the pieces. ADATA acts as a check for this. Before refinement starts, it looks again at the original task description, T-task, which lists all the data files. It then compares that list to what the initial solution script ESI is actually loading. If it finds important unused data, ADATA revises ESI to include it properly. In that Nomad 2018 example, ADATA made sure MLE-STAR loaded and used the geometry.xyz files with the atomic structure data, and as the results show, this led to a significant performance boost because the model finally had all the relevant information. ADATA ensures thoroughness.
So these robustness modules aren't just minor tweaks, they're smart components preventing common LLM errors, ensuring data integrity, and boosting reliability, building trust into the automation. Okay, with such a detailed architecture, the big question is obvious. How well does MLE-STAR actually perform? Let's get into the empirical validation on MLE-bench Lite. Tell us about the setup and the benchmarking.
Right, the experiments were set up for thorough validation. They ran across 22 diverse Kaggle competitions from MLE-bench Lite covering tabular, image, text, audio classification, even image-to-image tasks like denoising. To ensure results were reliable, each experiment used 3 different random seeds. The main LLM was Gemini 2.0 Flash, powerful but efficient. But we also tested others like Gemini 2.5 Pro and Claude Sonnet 4 to check generalizability. For an MLE-STAR itself, we set parameters to balance exploration and speed, 4 initial model candidates from our retriever. The refinement phase had 4 inner loops for refining one block and 4 outer loops for finding new blocks. For ensembling, it generated 2 solutions in parallel and explored ensemble plans for 5 rounds. Crucially, for fair comparison, there is a strict 24-hour time limit per task, matching the MLE-bench standard. And interestingly, despite its complex system, MLE-STAR actually took less time on average, about 14.1 hours, compared to the main baseline, AID, which took around 15.4 hours. So better performance and more efficient.
That's fascinating. Not just better, but faster too. That's a big practical plus. Who was the main baseline and why choose them?
The primary state-of-the-art baseline was AID. This was based on its strong reported performance on MLE-bench previously and its ability to handle diverse tasks. While other LLM agents exist, they often have limitations, making broad comparisons tricky. DS Agent, as we discussed, needs that manual case bank, so it's not really comparable on tasks like audio or image denoising, where cases might not exist. AutoGluon is great, but mostly optimized for tabular data, so AID was the most suitable general benchmark for an apples-to-apples comparison across the varied MLE-bench Lite tasks.
Makes sense. Okay, let's get to the brass tacks. The main quantitative results. What did Table 1 show about MLE-STAR's overall performance, especially the medal rate versus AID?
Table 1 showed really significant gains. Using Gemini 2.0 Flash, MLE-STAR boosted AID's any medal rate quite dramatically. It went from 25.8% for AID up to 43.9% for MLE-STAR. That's a solid 18 percentage point jump, a real shift in competitiveness. Even more impressively, the above median rate, meaning it beat the median human score, shot up from 39.4% for AID to 63.6% for MLE-STAR. That shows it's consistently producing highly competitive solutions.
And what about gold medals? That's the absolute top tier, right? Often matching top human experts.
Yes, and this is where it gets really interesting, highlighting MLE-STAR's design strength. Even using the more efficient Gemini 2.0 Flash, MLE-STAR actually outperformed AID when AID was running on a much larger, more powerful reasoning model like O1 Preview, specifically in getting gold medals. MLE-STAR got golds in 10 percentage points more tasks than AID using that stronger model. This really underlines that MLE-STAR's smart framework, the search, targeted refinement, lets it effectively use even less powerful base LLMs to get superior results. It's not just about raw LLM power, it's how the system orchestrates it.
That's strong proof of the framework's value. And speaking of power, how does MLE-STAR scale if you do give it a stronger LLM? Does it benefit from better underlying tech?
Absolutely, and it's another key finding showing its future-proof design. When we paired MLE-STAR with Gemini 2.5 Pro, a much more capable LLM than Flash, its any medal rate climbed over 60%, hitting 64% exactly. This clearly shows MLE-STAR's design can effectively harness improvements in reasoning-based LLMs. Its modular setup and feedback loops let it push performance boundaries as the underlying tech gets better, very adaptable.
Beyond AID, you also compared it to DS Agent on those tabular tasks where DS Agent should shine. How did it fare, especially considering DS Agent needs all that human effort for its case bank?
Right. On those 4 specific tabular tasks, wild blueberry yield, media campaign cost, spaceship Titanic, enzyme substrate, which DS Agent was developed on, MLE-STAR with Gemini 2.0 Flash significantly outperformed DS Agent. This is huge because MLE-STAR did it without any of the human effort needed for DS Agent's case curation. And what's more, as shown in Table 9 in the paper, MLE-STAR also beat AutoGluon on most of these tabular tasks. That's really notable since AutoGluon is specifically designed and highly optimized for tabular data. It shows MLE-STAR's general effectiveness, competing even against specialized tools on our home turf.
That really highlights its generalizability and efficiency. And on that note, how did it do with different LLM types, not just Gemini? Is the framework effective regardless of the vendor?
Yes, we checked that too. We tested its compatibility with Claude Sonnet 4 on a mix of tasks: image to image, denoising dirty documents, image classification, dog breed identification, text classification, spooky author identification, and audio, the iCamel 2013 Whale Challenge. The results were consistently strong, showing MLE-STAR maintains effective performance across different LLM types. This versatility is a big practical advantage, meaning the framework isn't locked into one LLM family, more flexibility.
Okay, now let's unpack those ablation studies. They're key to understanding what parts of MLE-STAR really drive the performance. First, how did using different reasoning models like Pro versus Flash impact performance within the MLE-STAR framework?
The ablation on reasoning models clearly showed that a stronger LLM definitely amplifies MLE-STAR's power. power. Gemini 2.5 Pro consistently gave better results than Gemini 2.0 Flash within the framework. A really striking example was the denoising dirty documents competition. With Flash, MLE-STAR scored above median but got 0 medals. But switch the LLM to the more powerful Pro, and for that exact same task, MLE-STAR suddenly got 2 gold medals and 1 silver. That massive jump directly validates the design principle. MLE-STAR is built to effectively leverage better reasoning LLMs as they become available. The framework provides the structure, allowing a smarter LLM to perform better within each agent's role, like Appable finding better ablation points or a coder making smarter refinements.
That's a strong sign the framework itself enables ongoing improvement. And finally, that novel ensemble method. How much did that specific contribution add to the overall gains?
The ensemble method turned out to be a surprisingly significant boost. The ablations in Table 4 showed that even without the special ensemble strategy, MLE-STAR was already beating aids significantly over 12 percentage points better in any medal rate. 38%, 5 artists, 25.8%. That alone showed the power of the search and refinement. But then, when we applied MLE-STAR's novel ensembling procedure, the performance jumped again. The any medal rate climbed to that 43.9%, and it consistently improved the gold medal rate too. This advanced ensembling pushed performance even further beyond the median human expert. And while simpler ensembles like best of n, just pick the best single solution, or a basic average ensemble did help compared to single models, MLE-STAR's proposed method, with the AMPS planner exploring strategies, was demonstrably more effective. It got more gold medals and a better overall success rate. This really validates having the agent autonomously figure out the best way to combine its solutions, rather than using fixed rules. It's learning how to ensemble optimally.
Okay, that covers the numbers and the how. Now let's shift to the why and the so what. Digging into the qualitative insights and bigger implications. Why does MLE-STAR do so well? What did those observations on model usage in Figure 4 tell us?
Yeah, the qualitative look at model usage gives a really clear picture, especially in Figure 4 for image classification. AID, the baseline, heavily favored older models like ResNet from 2015. About 75% of its choices for image tasks were ResNet, which, was great then, but it's suboptimal now compared to newer stuff. This directly reflects that static knowledge cutoff. But MLE-STAR, thanks to our retriever searching the web for the latest stuff, it mostly used more recent high-performing models. Like it used EfficientNet from 2019 about 28% of the time, and Vision Transformers, or VIT, from 2020 about 27% of the time. This access to and use of current state-of-the-art models directly led to better performance. MLE-STAR got medals in 37% of image classification challenges, way better than AID's 26%. It vividly shows the value of that search as a tool approach. It finds the right modern solutions that the base LLM might not even know about, like using today's research papers instead of an old textbook.
So it's not just finding a model, but finding the right current model. Powerful argument for dynamic knowledge. And what about human collaboration? Is it fully autonomous, or can humans jump in?
While it aims for high autonomy, it's definitely designed for seamless human intervention. It fosters collaboration, which is crucial for real-world use. Humans still have valuable knowledge. Figure 5 shows this well. A user can manually give it info about a new or niche model, like Real MLP from 2024. Even if a retriever didn't find Real MLP via search, MLE-STAR can integrate it based on that human input. Shows its flexibility. Plus, users can manually point it to specific code blocks for refinement, like an engineer saying, hey, I think the bottleneck is this data augmentation block, focus here. This guided autonomy lets experts steer the process when needed, combining human intuition with the agent's power.
That's key for practical adoption automation that still allows expert guidance. Best of both worlds. Let's revisit those LLM misbehaviors and guardrails with more detail. Data leakage correction. How does a leakage actually spot and fix using test data wrongly in pre-processing?
Right. That's one of the most dangerous LLM hallucinations. Figure 6 shows an example. An LLM might write code that calculates scaling parameters or imputation values using stats from the combined train and test sets. Sneaky leakage. A leakage specifically extracts and analyzes the CDA block with the preprocessing code. It uses pattern recognition and context to spot these issues, like is fit being called on combined data frame. Our test labels used in training feature engineering. If it finds leakage, it generates a corrected HISCIDE, making sure stats, mean, variance, etc., are calculated only from training data before being applied everywhere. And this proactive fix is vital. As Table 5 showed, without a leakage, validation accuracy might look good. Example, jump from 0.8188 to 0.8677. But true test accuracy would crash. Example, 0.8033 down to 0.7343, because the model cheated by seeing pest data during training. The paper gives that example of using the transported target variable during feature engineering. A leakage catches that, preventing a model that looks good internally but fails externally.
So it stops real damaging errors that inflate metrics but kill real-world performance, and ensuring full data use. LLMs sometimes miss data files. How does Adata fix that oversight?
Adata tackles that common issue of ignoring some provided data. Complex Kaggle comps often have multiple files, like in Nomad 2018 predicting there were crucial geometry.xyz files with atomic structures alongside CSVs. An LLM might just load the CSVs, ignoring the vital.xyz files, maybe due to bias towards common formats. Figure 7 shows this. Adata acts as a check. Early on, it rereads the task description t-task, comparing the listed data sources to what the initial script 0 actually loads. If important data is missing, Adata revises dead 0 to include it. In the Nomad 2018 case, Adata made sure MLE-STAR loaded and used those geometry.xyz files, and Table 6 shows this led to a significant performance jump because the model finally had all the necessary info. It ensures nothing gets left behind.
These modules really elevate MLE-STAR beyond just code generation to a reliable engineering agent, essential quality control. Finally, the improvement trajectory. Does it consistently get better through refinement?
Yes, remarkably consistently, as Figure 8 illustrates nicely. That plots the average relative error reduction across all 22 challenges as refinement progresses. You see steady improvement with each step, and what's striking is how much improvement happens early on. The biggest jumps are often in the first few outer loops. We think this is down to the ablation study module. By testing components, Able and Extractor effectively find the most influential blocks, the bottlenecks, or low-hanging fruit first. By hitting those high-impact areas early, MLE-STAR makes big gains efficiently before moving to finer tuning. Smart prioritization.
Powerful confirmation of its strategy. Before we wrap up, let's touch on limitations. Kaggle comps are public. Could the LM have just seen solutions during training? How novel are MLE-STAR's outputs?
That's a really valid concern with public benchmarks. There's always a risk the LLM saw discussions or solutions during its training. Is it solving or just recalling? The researchers address this cleverly. They use another capable LLM, Gemini 2.5 Pro, as an independent judge. This judge compared MLE-STAR's solutions to top public Kaggle posts and solutions for the same challenges. The key finding: MLE-STAR's solutions were consistently judged sufficiently novel. They weren't just copies or slight tweaks of public stuff. This suggests that while the LLM has general knowledge, MLE-STAR's specific search, ablation, and refinement process leads it to generate unique, non-memorized solutions, mitigates the copy-paste concern.
So, genuine generation and innovation, not just regurgitation. Critical distinction. Well, this has been an incredibly insightful deep dive into MLE-STAR. To wrap it all up for everyone listening, let's recap the key takeaways. MLE-STAR is this novel MLE agent for diverse tasks. Its core strength: combining external web search for current techniques with systematic, targeted code block refinement guided by ablation studies. This directly tackles the old problems of static LLM knowledge and inefficient, broad exploration.
And the results on MLE-bench Lite really back it up. Medals in 64% of competitions, 36% gold. That's seriously impressive. It significantly beats baselines, even specialized ones, often more efficiently. The multi-agent setup, the dynamic knowledge integration, the refinement loops, those crucial guardrails like a leakage and a data, they all work together for superior, reliable performance. It feels like a real leap forward.
So what's the so what for you, our listener? Whether you're a data scientist fighting for leaderboard spots, an MLOps engineer streamlining pipelines, or just fascinated by AI's edge, this deep dive shows a massive step towards truly autonomous ML development. It demonstrates how integrating dynamic knowledge and targeted refinement lets agents automate complex work and achieve competitive, state-of-the-art results. It frees up human time and hints at a future where agents do more of the initial heavy lifting.
Which leads to that profound question about the future role of human experts. If agents like MLE-STAR not only master current techniques via search, but also adapt to future ones as they emerge, what does that mean for us? Do we shift from coding and tuning to being higher-level architects, problem definers, maybe meta-supervisors, guiding these agents on truly novel or complex problems they still struggle with? It's a fascinating shift towards collaboration focused more on strategy and boundary pushing, less on pure execution.
A really thought-provoking idea to mull over. Thank you for joining us on this exploration of MLE-STAR. We'll be back soon with another deep dive into knowledge and innovation.